So just before we start, I wanted to make a few announcements. First is that this list will be here until the beginning or tomorrow.
Want to say? No, leave it. Don't touch it. Just tell me when I can start.
Well, so welcome then to the morning session, and our first speaker of the session is Altland,
Nothing.
The title is
That is fine. Yeah, good morning, everybody. We just heard it. I mean, a long, long day ahead. So let's start very slowly. What I would like to do in this talk is review elements of SYK physics of the SYK model, from a perspective that hopefully resonates with an audience that is inclined to semi-classical analysis and chaos. Yeah? Now, in that mindset, from that perspective, what makes the SYK stand out is that it is a model of many-body quantum chaos, which, on the one hand, is complex enough to display really the full richness of many-body chaotic correlations, and at the same time simply enough to be amenable to numerical and analytical approaches to the extent that you can actually compare analytics and numerics in parameter-free manners. And that makes it kind of unique and has made it a focal point of interest to the general community of many-body physics, quantum chaos, condensed matter physics. I should also add for completeness that the SYK affords an holographic interpretation, or so we hope, as a boundary of an two-dimensional ADS bulk, but I will not focus on that aspect. It will shine through every once in a while today, but I really want to focus on the chaos and correlation aspect. Now, the way the talk is organized, I will first introduce the model, not assuming any previous knowledge, and then we will see that it makes sense to discuss its physics, its dynamics, separately for short times. I will define what short means, where we see all kinds of exponential instabilities and collective quantum fluctuations. And then in the main part of the talk, I will focus on long times comparable to the many-body Heisenberg time of the system, where we can look at spectral and wave function correlations. And I want to emphasize aspects of semi-classical, if you want, semi-classical analysis, and in particular, the physics of orbits in Fock spaces. Okay, so that's kind of the plan. Now let me start introducing the model. It shouldn't be called SYK, actually, because, well, I mean, let me first tell you what it is. it's SYK is a representative of a larger class of models, which one can call random interaction models. And random interaction models are models of pair or higher order interacting bosons or fermions. Everybody talks to everybody. And these interaction constants here are drawn from a random static distribution, typically a Gaussian distribution. And these models, as many of you here will know, were actually pioneered by one of our godfathers in this community, by Oriol Bohigas, in the early 70s, where they were employed to model or describe the physics of complex nuclei in a manner somewhat more refined than a straightforward random matrix approach, and that defined the field of embedded ensembles, which, I mean, hope it's fair to say, I mean, picked off in the 70s, but really didn't get very far at the time. I mean, computers were small and slow, and analytical progress was considered impossible at that time. Now, there came a second incarnation in the early 90s. In the early 90s, the model was rediscovered by Sachdev-Ye now in the context of condensed matter physics. They were looking at strongly correlated magnets. They did not know about the earlier realization in nuclear physics, but they discovered something extremely important which has been missed before, namely that these models support a very high degree of symmetry in approximately realized infinite-dimensional conformal symmetry, which overshadows the entire physics at low energies, and we will see how this comes about. And then came a third incarnation, rather late now, in 2015 by Kitaev. That's why it's called Sachdev-Ye-Kitaev, and Oriol Bohigas is missing. What he proposed was to look at a system of interacting Majorana fermions, I mean real fermions, and the motivation came from holography. But from a many-body perspective, what makes this model really interesting is that this system here is qualitatively easier to analyze. It's a massively interacting system, but it's much easier to analyze than bosonic or fermionic systems. And this simplicity is rooted in the simplicity of the Majorana-Clifford algebra, which is simpler than the Heisenberg algebra. So that's the one where we can actually do a lot analytically, and this simple Hamiltonian now really, I mean, is interesting in that it, it connects to the physics of quantum chaos, strong correlation physics, and then there is this holographic angle. Now let's try to get closer to the physics of this Hamiltonian, and it actually makes sense to organize this discussion. I mentioned it on a timeline from short to very long times, where we have at least two fundamental scales to distinguish. Here is time scales of the order of n. N is the number of Majoranas, the number of constituents in the system. And we will see that here the physics is kind of, close to classical in some sense, and here strong quantum fluctuations take over. I will show how. And then at much, much, much larger times, we have the Heisenberg time of the many-body spectrum, where we can see spectral correlation and the approach to ergodicity in the system. Yeah? And both, large and small times come with their own characteristic phenomena. Here we see exponential instability. These days, people like to call this scrambling for whatever reasons. Then we see the conformal symmetry here at work, and we have here strong collective quantum fluctuations developing. And at large times, we have quantum ergodicity, collective spectral fluctuations, the analog of diffusion modes in the system, which actually drives the approach to ergodicity and another type of symmetry breaking. Now, from a technical point of view, what's good is that we have actually two powerful analytical approaches to attack the system from two directions. Here, at short times, we have what is called in the community the G-sigma formalism. I will briefly show you what it is. And it works best for very short times. And out here, we have a version of a nonlinear sigma model, which works best at asymptotically long times. So we have a pair of pincers, and we can come from two directions, which gives us some leverage. And let me now first say a few words on this short-time-ish physics, because motivated mainly because it connects to earlier talks we had here. And then in the main part, I turn to long times. So short-time dynamics, what people do here is, more or less obvious. They look at the thermal trace of the Hamiltonian, some kind of partition function, average over disorder. And this averaged object is then represented as a path integral. And I will not introduce this path integral here in any detail. It has an explicit form, this kind of monstrous form down there. It's an exact representation. But what's important to know is that there is some functional integral exactly representing this partition function, and there is an action sitting here, and what's important is that this action has a factor n up front. And that begs for a mean field approach, yeah? A large n stabilized mean field approach. Yeah. Yeah. Because, yeah, I'm neglecting replicas here. So I'm sweeping them under the rug. I mean, it's a log of the partition function, actually. But not to overburden this. There is a replica structure sitting here, which I'm just sweeping under the rug. Now, what do we learn if we, I'm just telling you, what do we learn if we do mean field? Extremize this functional integral. The first object to look at is the Majorana correlation function, the green function if you want, 2-point function in the system. And what you find in a mean field approach is that it shows some square root behavior. And that is, I mean, people in condensed matter love this because this is indicative of strong non-Fermi liquid behavior. Yeah? So the particles in the system are very different from those in a weakly disordered or weakly interacting metal. They have this strong non-analytic behavior, non-Fermi liquid behavior. That's number one. And number two, you then turn again within this mean field approach to, I mean, you want to diagnose first traces of chaos, and one of our friends here is the out-of-time correlation function. We heard a lot about that yesterday, now applied to this system, where you probe the fidelity of two states, differing just in the order of two operators applied to the system. And you can do this now for this, in this context, and the obvious choice of these operators now are the Majoranas themselves. So you compute an OTOC, where instead of coordinate and momentum, you take two different Majoranas. And then compute this trace within the mean field analysis of this path integral I mentioned. And what you then find is something which makes these holography people excited. Namely, you find an exponential behavior, and the coefficient, what they call Lyapunov exponent, is indeed temperature. And that is the chaos bound of Maldacena. So the interpretation, the folklore in this community is that this system is as chaotic as it possibly gets. And they love that because that would be, sit nicely, comfortably with the presence of a black hole in an ADS bulk. Yeah? So, but from a more operational point of view, this is what they get from this functional. So this rushes now down exponentially. It would like to hit the ground at a scale log n. Think of this m here as essentially as n. But one then finds that at somewhat larger time scale, it trades out exponentially. And now one can ask what happens. I mean, this is like sort of this exponential behavior we saw many times yesterday. And a natural guess would be it goes on forever. But at some point, at some time scale, comparable to m or n, the semi-classical analysis loses its meaning. You can no longer work semi-classically. You get, I mean, your path integral shows strong fluctuations. And it then turns out, and that is the one thing I wanted to communicate here, that at long time scales, the OTOC actually becomes power law. So you have a crossover from exponential behavior at short times to a quantum-dominated power law, and these quantum fluctuations are sort of more mellow than classical fluctuations, and this is what you get. Yeah? And one challenge in this holographic game is to explain these power laws from a bulk perspective, but that's that. And that is as much as I wanted to say about, just by way of orientation, about short-time behavior, but let me now focus on long times. So now we totally switch gear. We forget time. We think more in an energy-oriented way. So small energies comparable to the Heisenberg time. And the focus is now on this long-time regime. And the first thing to look at is numerical data, which we have for systems of n about 34, 36, so that is state of the art. And what you see there is beautiful random matrix correlation. So the usual suspects, spacing distribution, number variance, or this is a form factor here. They look pretty random matrix-like, so you would say, aha, at long time scales I have quantum ergodicity in the system, which is natural. But then there is a little bit of interesting fine print. If you look closer, you see that actually there are deviations from random matrix. So here, for example, you get this upturn in the number variance, which is more pronounced for smallish systems. Or in the form factor, here, you have this funny upturn at times which are, well, that's actually a matter of debate, or of what times. And these are universal, yet non-random matrix additions to spectral correlations. And one of the challenges is to understand where they come from and what is the universal physics sitting there. And form factor, spectral form factor. This, which normally has this. So we want to understand the physics of these deviations, and so these are these corrections. And for that, we look at, it flashed up, at the spectral two-point function now. Spectral two-point function. And to get the spectral two-point function of this system under control, we take a somewhat crazy perspective, or somewhat funny approach. Namely, we think of the SYK Hamiltonian as a matrix. I mean, from a first quantized perspective, yeah, it's a many-body Hamiltonian, but I mean, can represent it formally as a big matrix, an exponentially large Hilbert space. And in this mindset, the essential information is encoded in the resolvent of this Hamilton operator. Now, normally, for a plain vanilla, I mean, many-body system, this is, of course, hopeless to do this. I mean, Hamiltonian is sparse, it is highly correlated, it's high dimension, it's all what you don't want to have. But this system here is just simply enough that we can actually make some headway in this approach. So we do this, and we apply methods of single particle quantum disorder physics to this system. So let's see how this works. This leads then to some kind of semi-classical interpretation of spectral correlations. And to set the stage, I would like to remind you of how we would approach such a problem in the context of a simple disordered system. Say, think of a disordered metal for a moment. Yeah, so let's forget about SYK for a sec and ask how would we get spectral correlations in a disordered metal under control. And I present this in a language, in a manner which can then be easily, well, straightforwardly adjusted to Fock space. So that's a little recap, and I mean, I hope I don't bore you here. Suppose we have a metal, we want to know disordered spectral two-point function. The density of states represented as usual as a trace of the green function, and then we represent this semi-classically as a closed orbit in a disordered medium. Yeah, everybody knows this. Now we need two of these orbits because we have two density of states, and our leading contribution to the spectral function under a disordered average will be Michael Barry's diagonal approximation, now transferred to a disordered medium, yeah, where it's called Altschuler-Stokowski diagonal. So let's try to compute this. I mean, how do we do that? If we look a little closer in what's going on here, we have here pair propagating retarded and advanced amplitudes scattering. There's a prime down here missing. So scattering at realizations of a random potential. And if this random potential is finite correlated, these points will be close but not identical to each other. There is some correlation length which governs their proximity, so that's why I drew this here in irregular forms. It's not like a nice periodic orbit pair, a little bit more dirty. And now you want to sum over these contributions. And the essential observation you make now to actually get this under control is that there is a conservation law around. The conservation law is the following. Rather than working in coordinate space, it's much better to go to momentum space and to realize that the relative momentum of these two lines is conserved. Each scattering process, its momentum conservation conserves this, and the physics is that on average a disordered medium looks translationally invariant. So you have this conservation law. And one way of putting this is that it actually makes sense to go from a real space representation of bras and cats. So think of this, actually this bra-cat pair here as a matrix acting in a Hilbert space. You switch to a different matrix representation now in terms of momentum eigenstates, right? And if we do that, if we apply this kind of, think of it as a basis change, then we are in business. Then we realize that our ladder of scattering processes is characterized by a single conserved quantum number, Q, the momentum difference. It labels them. You can compute the decay constants or you can compute these diagrams. You identify decay constant dq squared plus I omega, which tells you that this is a diffusive stochastic process which we are dealing with. And importantly, these Qs are quantized. In a finite size system, they are quantized due to boundary conditions, 2 pi over L times some integer. So that's what we know. And physically, these are irreversible relaxation modes in the medium. And if you now sum over these modes, you get the following structure, which is, again, I mean, this is essentially the pair correlations in periodic orbits in diagonal approximation, now adjusted to this context here. So you have a sum, you have two of these modes, this one here and that one out here, characterized by their eigenvalues, two of them squared, you sum over them, and you get this term. Now, a little care must be invested in understanding the q equals 0 term. For q equals 0, you have a divergence for small omega, but then everybody here understands that this process here is only the first of a whole series of higher processes of higher order complexity, processes that contain encounter regions. So this is, in periodic orbit languages, would be the whole series of pairs of orbits containing encounters. And if you sum over them, we know and understand that in the end of the day, after a lot of work, we get random matrix. Yeah, so the omega equals 0 contribution is actually the RMT. And this is then spectral statistics. Was it clear, more or less? For disordered metal. Now let's play the same game in Fock space and see how far we get with that. Yeah. Again, I mean, to remind you, the perspective is we think of our many-body Hamiltonian as a matrix, and we want to know the green function, pairs of green functions correlated. And what we will massively exploit now is the simplicity of the Majorana-Clifford algebra. And well, I mean, to set the stage, now we are no longer dealing with this disordered metal Hamiltonian, but our friend, I mean, SYK Hamiltonian. And to simplify the notation a little, I represent this guy as a sum over all quadruples of indices, everybody running from 1 to n. There are here these coupling constants, random, JA, and there is this quartic product XA. So that's the Hamiltonian. And now we can write down a table, just a translation table that tells us how we should translate from single particle physics to this framework. So let's go through the entries. A Hilbert space in a dirty metal or chaotic single particle system function space, L2 functions. Here we are dealing with a Fock space of what? Of n over 2 fermions. So out of n Majoranas, you can produce n fermions. Yeah, I mean, chi plus I chi prime gives you a fermion, complex fermion. So the Fock space is one of n over 2 complex fermions, and as such, it is 2 to the n over 2-dimensional, finite dimensional Fock space, replacing now the infinite dimensional function space. Now, what was a good native basis to work in? I mean, here we work in a position basis to begin with. Here, a good basis, natural basis, is what is called the computational basis. This is just the the occupation number basis of these fermions. Each fermion can be occupied or non-occupied, so we work with binary words of zeros and ones. These are the bases, 2 to the n over 2 of them. Then let's naively assume that, again, I mean, our dominant contribution to spectral statistics will come from pair-correlated diagonal approximation-like passes in Fock space, in which case this scattering vertex here gets now replaced by what? By Fock space states scattering of these operators here. So you have a Fock space state n, it then scatters of one of those, or it's correlated to n prime and double prime and so on. And now we realize we are in trouble at this point, because this animal here is massively non-local in Fock space. So you have no sense of closeness of these orbits. And anyway, the relevant contributions, phase-coherent contributions, can be as far as you want in the norm of the natural norm of this hypercubical Fock space. So that's a challenge, getting this under control. Yeah? But then there is the idea that perhaps we can play a similar game like here and apply a clever basis change. So here, to remind you, we switched from coordinate basis to momentum states. And it turns out that in Fock space, you have a better basis to work with, and that's the key to progress. So instead of working with these brass and cats of Fock space states, 2 to the n of them, 2 to the n over 2 here, 2 to the n of here, we can switch to a different basis of Fock space matrices, and it's constructed as follows. You just take your Majorana operators, you have n of them, and build all possible products you can make. And since they square to 1, you have 2 to the n different products. And it is easy to see that these are matrices in Fock space, operators in Fock space. And it is easy to see that they form a complete set. So each of these states here can be expanded in those. And each of these matrix elements is labeled by a word, I mean, of zeros and ones. And they have a certain length. I mean, this would be a length k operator. So these are our friends. What we should do is work in the basis of these operators, and the intuition behind it is as follows. I mean, I just try to give you the idea why this is a good language. So think of a Fock space sequence of scattering states, and here another one, which is very complicated. And you see this complexity in the following, or can see it in the following way. If you expand this particle hole mode in n's and m's, and you let the scattering operators of the Hamiltonian act on it from left and right, you get different states here. So you have to do this bookkeeping. But suppose now we expand these n's and m's in these product bases of lots of Majoranas. And as such, we expand our particle hole mode in these operators. Then the action of the Hamiltonian will be just a sign factor. Why? Because the Majorana Hamiltonian contains the product of Majoranas itself, and they either commute or anti-commute with these guys. So you don't change the state. You only pick up a scattering phase. So this is really quite literally like a conserved momentum. If you start in one of these channels, you stay in it. And the only thing that can happen is that you pick up some eigenphase or some eigenvalue. So that's maybe a bit brief here, but this is the philosophy behind it. And if we do that, we can, I mean, you run a calculation, you see that these words of Majorana, they label each of these modes. We have lots of these modes. For each Majorana operator, we have one. They replace the diffusion modes. You can calculate their eigenvalues, their decay. And this you can be all done analytically. I mean, it's even quite easy. And you see that at for short words, this kind of it's the analog now of this Thouless or this diffusion eigenvalue here. They decay linearly in the length of these Majorana words. So a very long sequence of Majoranas will decay quickly. A short one will decay slower. And you have this under control. I mean, and here's a many-body level spacing as a reference scale popping up. So that's it. I mean, and now we can see how far we get with that. So we write down this semi-classical representation of the spectral two-point function, where again the zero mode, this is length, the ergodic mode, length 0 Majoranas is RMT. And now you have this sum over many, many modes. But the eigenvalues, the diffusion-like eigenvalues, depend only on the length of these Majorana words. So you have a combinatorial factor sitting here. I mean, this counts how many words you have of a given length. And here you have this decay constant, and that's it. So this is the formula. And now we can check if it works. Is that clear so far? Yeah. So let's now compare to results. And so this here is numerics for the spectral two-point function from Jacques Verberschott and Garcia. And this is what this formula predicts, and there is no parameter here. So this is a parameter-free comparison, and it's really spot on. I mean, Jacques tells us it's in the level of percent. I mean, so it's these corrections are clearly captured by this way of semi-classics. And another one is the form factor. So here, this is a standard, it's somewhat plotted in a funny way, but this is a standard RMT form factor that everybody knows for the unitary ensemble. And if we sum over these modes here, we get this upturn, and it, again, compares very favorably with the numerics. I should add one word. I mean, normally you would say, if there are these relaxation modes around, and there's many of them, there's combinatorially many, and most of them decay very quickly. There should be something like a Thouless energy. I mean, a universal scale, energy scale or time scale, above which a random matrix theory no longer applies. Oh, I'm not saying that. I'm not saying that. They are they become meaningless. Yeah. But here you are already at time scales shorter than the inverse bandwidth of the spectrum. So it's totally meaningless. What's happening here is unphysical. I don't know why they plot it in these numerical papers. So you're right, you understand. I mean, you have a certain bandwidth, and in principle, you can write down timescales shorter than that, the inverse of that, but they are not resolved. And it's if you plot it, I think we have even some. So it's not here, but it's somewhere here. You have this. You're losing this. So it's kind. That's why I'm saying it's somewhat difficult to compare this. Right. So one thing to notice here is that in this business there is no universal Thouless energy. Depending on which observable you look at, you get different answers for the time or energy scales where ergodicity breaks down. And that has to do with the fact that you have combinatorially many of these modes. And I can explain this point if anybody is interested. Just one thing to notice. Okay, so that was spectral statistics. Let me, what's the physics of these modes? And actually, the physics was understood quite a while ago by Thomas Seligman, the qualitative physics behind it. I mean, we have here this representation of the spectral two-point function again. And one way of putting it is that in a single particle of low-dimensional chaotic Hilbert spaces, if you look at density of states, we tend to have these hard edges, semicircular type of behavior. Now, in many body systems, in the embedded ensembles, the spectrum looks much more slack. On average, you get typically, tails in distribution functions, Gaussian, density of states which are Gaussian here in the center and have long tails. And somehow the physics behind it is that you don't have so much statistics in this system. You have only algebraically few independent matrix elements. The Hamiltonian has n to the 4 terms, but you have an exponentially high-dimensional matrix. So the matrix is massively statistically correlated, and Thomas interpreted this, the consequence of this, as the presence of some large-scale mesoscopic collective fluctuations in the spectrum, which make it soft. So the spectrum is basically wobbling back and forth, and that's the physics of these modes. So there is no big deal, and they create. In the number variance, you may have noticed the number variance increased quadratically in n. It's super Poissonian increase in the number variance. The spectrum is massively soft, and this is the. And I think it's pretty generic in many body systems that we have this behavior. Okay, so that was that. Now let me say a few words on wave function statistics in this system. So we heard a lot about that yesterday. That's we can add some remarks here from this perspective. So just to set the stage again, we in condensed matter business or disordered systems, we as of 2005 we grew used to many-body localization, which essentially tells us that in a disordered many-body system we can have phase transitions between strong disordered MBL phases where you're localized, wave functions are localized and you have Poisson spectral statistics, as opposed to low disordered systems where you're ergodic and have Wigner-Dyson. Yeah? Now, rather more recently, in 2015, people came up with the idea that this might be too coarse, this distinction, and that, generically or not, between the Poisson phase and the ergodic Wigner-Dyson phase, there might be another Wigner-Dyson phase where you spectrum is Wigner-Dyson-ish, but your wave functions are no longer ergodic. And the question is, are these phases around? Are they ergodic? Are these crossovers or not? This is all very murky, I understand, and we heard about this yesterday. It's a very difficult problem to get this under control. And what people often do is, because many-body systems, real many-body systems are too complicated, they look at effective systems. And one of these effective systems are the random regular graphs. So graphs which basically in a cartoonish way look like this: constant coordination number, random geometry, and some disorder added. The idea here being that somehow they mimic the complexity of a Fock space. And you can hope that, and they're a little easier to analyze, but still very complicated, and we heard that there is a debate going on, actually a battle between two Russian camps, which one says it's ergodic, and another one it's non-ergodic. And they all have very good arguments. A much simpler paradigm, which we heard about it yesterday, Martin talked about and also Eugene, is the Rosenzweig-Porter random matrix plus a diagonal. Plus a diagonal, and if you ramp up this diagonal, you are basically, you localize on the eigenstates on the diagonal, and if it's absent, you have ergodicity. So, to remind you, what's going on in the Rosenzweig-Porter is, if we add this diagonal and scale it with a certain power of the dimension, we actually have three phases. There is a Wigner-Dyson ergodic phase for, anyway, sub-extensive behavior of gamma, I mean, where you don't scale smaller than 0. Then you have a wide intermediate regime where you still have Wigner-Dyson statistics, but you have fractal, not multifractal, but fractal behavior of the wave functions of these moments here. And it was all explained yesterday. And then at very strong diagonals, you go into Poisson. And this has been established in different ways, and one of them being supersymmetric nonlinear sigma model, this beautiful paper which shows this in very short calculation you can get this from. And the idea is now to ask, can we see such phenomena in this many-body system in SYK? And to this end, we did the following. We took plain vanilla SYK and perturb it now with a actually somewhat stupid operator, but it's one we can get nicely under control. It goes as follows. You add a diagonal, Fock-space diagonal operator, obtained as follows. You sum over all computational states, all occupation number states, and you weigh them with random coefficients and average. And why would one do that? Well, I mean, the picture should be clear enough. In SYK, you have ergodic wave functions uniformly distributed. If you have just this operator, you are localized in Fock space on these 2 to the n states. And in intermediate regimes, the way I like to think about it is as SYK is a distance 4, it can change the occupation number only up to a maximum of 4. So it's a kind of a band matrix-like operator acting on these localized states. And it is clear that there is a transition going on between localization and ergodicity. But the question is are there traces of wave functions, interesting wave function statistics? And I want to spare you the details, but I mean, in the background we have, including what I said earlier about these diagrams, we have a replica nonlinear sigma model at work, and we applied it to this setting, and the predictions are as follows. If you ramp up the strength of the diagonal, and you have a relatively wide window, the diagonal being up to order n squared times larger than the SYK bandwidth. Yep. So for a rather large interval, you can actually map the perturbed SYK to Rosenzweig-Porter, and that's essentially it. I mean, this is a statement. This means you have a robust mapping of this complex system to a much, much simpler random matrix model. And that implies, I mean, just now translating from what we had yesterday, that for diagonals larger than 1 in units of the SYK bandwidth, we enter a phase of weak non-ergodic fractality. And for larger values, we go into a Fock space localized. Yeah, so this is a prediction. One can make this more quantitative. I mean, we just forget this formula. I mean, but I just want to show there is an analytic formula which we get from this formalism. From the analysis of wave functions in this case, and we get 3 different regimes where you have the many-body level spacing popping up, and here the dimension of your matrices 2 to the n, and the strength of the diagonal. And yeah, this is comparing to numerics. I mean, so here's the strength of the diagonal. The green dashed line would be, this is now the inverse participation ratio, the fourth moment of wave functions. And the green line is RMT. Then you get deviations, and the black is analytics, and the crosses are numerics. And here our several things break down. I mean, here you get, it's all logarithmically close here, but you get breakdown of our modeling, you get the onset of localization, and I mean, nothing should agree anymore. But up to this point, we have good agreement. Here, you see the Kullback-Leibler entropy, which basically tells us that up to this threshold here, we have RMT statistics. So this is the fidelity of RMT, and beyond it, we have Poisson. So there's really kind of a phase transition, if you want, going on here in this region. But this is a regime where we get these deviations of wave functions from ergodicity. It's relatively mild. I mean, it's not, so they are, because we are working with very high dimensional matrices, and these deviations are all expressed in powers of n. But still, it's, actually, this is all very fresh, and I don't know yet really how to interpret this in good ways. But I would like to just demonstrate here that one can actually get this analytically for a many-body system. Okay, and that's essentially it. I mean, I wanted to convey that this SYK setting is a useful playground for many-body quantum chaos. It really sits at a sweet spot between complexity and of phenomena and complexity of its analytical understanding. We have all these phenomena related to chaos, instabilities, and quantum fluctuations, and God knows what. It's very good for comparing numerics and analytics. For example, periodic orbits, box spaces. This is where one can play nicely with it. And then there is, of course, all the ramifications in holography, which is a whole different story. I mean, which are not for here, but they exist in addition to that. Okay, that was all. Thank you very much.
In your model,